Today I'll talk about mole concept. I'll talk about mole, Avogadro's number, molar mass and mole fraction. What is mole concept? The mole concept is a fundamental principle in chemistry that relates the mass of a substance to the number of particles it contains. It is based on the concept of a mole, which is a unit used to quantify the amount of a substance. Now here we must remember some key point of the mole concept. First is Avogadro's number. The mole is defined as the amount of substance that contains the same number of entities. Entities like atoms, molecules, ions or other particle, as there are atoms in exactly 12 grams of carbon 12. This number of entities is approximately 6.023 or 6.02223 into 10 to the power 23 and is known as Avogadro's number. Means in 12 gram carbon atom, in 12 gram of carbon 12 has 6.023 into 10 to the power 23 number of entities. So that 6.023 into 10 to the power 23 is actually Avogadro's number and its symbol is actually Na. Now coming to the 1 mole. 1 mole of any substance contains Avogadro's number of particles. So for example, 1 mole of atom contains 6.022 into 10 to the power 23 atom. Means 1 mole contains this number of atoms and 1 moles of molecule contains 6.022 into 10 to the power 23 molecules. That can be 22 or 23 that you can consider. Now here mole concept. Now here suppose if we take 12 gram of carbon, so that 12 gram of carbon means carbon atomic mass is 12 gram. So if you take 12 gram of carbon, that is called 1 mole of carbon, and that 12 gram of carbon 12 gram mass of carbon contains 6.023 into 10 to the power 23 number of atoms. Similarly, 1 mole of copper means 63.5 gram of copper, and that 1 mole copper has 6.023 into 10 to the power 23 number of atoms. Now other key points like molar mass. The molar mass of a substance is the mass of 1 mole of that substance expressed in grams per mole. Means 1 mole, how many grams is there? So that is actually called molar mass. The molar mass is numerically equal to the atomic or molecular mass of the substance. Now conversion between moles and mass. The mole concept allows for easy conversion between the mass of substance and the number of moles that it contains using the molar mass. The number of moles N can be calculated using the formula. So number of moles, that mass of substance gram by molar mass of the substance, that is gram per mole. Now coming to the molecular mass. Molecular mass, also known as molecular weight or formula weight, is the sum of the atomic masses of all atoms present in a molecule. It is expressed in atomic mass unit AMU or in grams per mole. Now here the relation is given. Now that moles, number of moles, if we want to calculate from number of moles to gram, so we have to multiply in molecular mass. If I divide mass in grams by molecular mass, so we will get number of moles. Similarly, if we multiply by Avogadro number with number of moles, we will get total number of molecules. If total number of molecules is given, so if I divide with Avogadro number, we will get moles of number of moles. Here if we divide mass in grams by molecular mass by Na, so we will get number of molecules, and if we multiply it with that molecules that Ma into Na with number of molecules, so we will get mass in grams. So this is very good relation So if we remember, so we can understood many things, and we can, it is required when we do some calculation. Now here the formula I am giving. So now n is w by m, w is n into m. So now from this correlation we can get the formula. N means molecule, number of molecules, in n small n, number of moles into Avogadro number. The small n will be the number of molecules by Avogadro number. So these are the formula. So capital N, again number of molecules, into w by m by na, divide w is capital N into m by na. Okay, now we are taking one example, like so carbon molecular mass is 12 and Avogadro number Na is, we know that. Now number of moles, we are taking 1 moles of carbon. So 1 mole of carbon if we take, so now if want to calculate W, so N is 1 and M is molecular weight. So N 1 into 12, so that will give the 12 gram of carbon. Now if I want to calculate, so from here so here mole, number of moles is 1 gram, 1 mole carbon. So from that we can calculate mass in grams. We also calculate number of molecules, how many number of molecules. So here everything is connected. So again this diagram is very much important. So if you understood this diagram, so it will be very useful for the calculation, means it will be very useful for the calculation in the process calculation. Means in the process calculation math you can easily do if you understood this concept. Now here, now I'm talking about mole fraction. Now in a container, two components are there, A and B. That Na is mole of component A in the mixture and Nb is the mole of component B in the mixture. Now what will be the mole fraction? A, mole fraction X A, that is denoted as XA. So moles of A and total moles of all component in the mixture. Now here only two components are there, so Na plus Nb. If there are more components, so that will be ... Okay, so more than. And mole fraction of B, so moles of B by total moles of component in the mixture, so Na by Na plus B. And remember, the sum of mole fraction of all component in the mixture is equal to 1. So after doing the calculation, after calculating the mole fraction, so if we add all these mole fraction, that must be equal to 1. If it is 1, then our calculation is okay, otherwise we have to check the calculation. Now here that one question is there, calculate the molecular mass of H2SO4. Now we know atomic mass unit, hydrogen as atomic weight is 1.008, sulfur 32.06, oxygen 16.00 mu. So molecular mass of H2SO4, so 2 hydrogen is there, 1 sulfur and oxygen 4. So 2 into 1.008, 32.06 mu, 4 into 6. So if we do the calculation, we will get 98.076 AMU. So molecular mass of H2SO4 is approximately 98.076 AMU. Now suppose number of molecules calculation. Suppose we have 3 moles of substance. We want to calculate the number of molecules in these 3 moles. So to calculate the number of molecules, we can use Avogadro number, which is approximately 6.022 into 10 to the power 23 molecules per mole. Now number of molecules, so number of moles into Na. So here 3 moles are there and Na is 6.022 into 10 to the power 3. So we can calculate number of molecules. So that will be 1.8066 into 10 to the power 24 molecules. Now number of mole calculation. Suppose we have sample substance X with a mass of 64 grams. We want to calculate the number of moles of the substance X. So the calculate number of moles, we can use the formula. So number of moles, mass of the substance by molar mass of the substance. So we need, so mass of the substance is 64, so we need molar mass of substance. So that is actually given, suppose 16. So we can calculate number of moles, 664 by 16, 4 moles. Small maths. Now calculate mole fraction of the mole fraction. Suppose we have liquid mixture containing 20 moles A and 30 moles B. So mole fraction of XA will be Na by Na plus B, 20 by 20 plus 30, so 0.4. And mole fraction of XB, so NB by Na plus NB, so 30 by 20 plus 30, so 30 by 56. Now if we add the 2 mole fraction, so that will be 1. So that is important. Now that in this liquid mixture, the mole fraction of liquid A means 0.4 means 40% A, and mole fraction of liquid B is 0.6, so means 60%. Means in that mixture, liquid mixture, 40% A is there and 60% B is there. So if we know the mole fraction, we can convert in the percent. If we multiply it with the 100, so that will be the percentage in that mixture. Now here number of moles at STP. So STP means we know standard temperature and pressure is defined as the temperature of 0 degree Celsius gas, means 273.15 Kelvin, and pressure is 1 atm, right? Suppose we have 22.4 liter gas at STP. So why we want to calculate number of moles of this gas? At STP, 1 mole of any ideal gas occupies 22.4 liter of volume. So remember that. That is very important. Means 1 mole at STP means 24 liters of volume. This means that number of moles of the gas can be calculated as number of moles. So volume of gas in liters by 22.4 liters of the mole. When we are taking that volume of the gas, so we have to take at STP. Otherwise, it will not be valid, because temperature and pressure, the volume will change. So given that we have 22.4 liter of the gas, so number of moles 22.4 by 22 for 1 mole. Means at STP 22.4 liters of the gas correspond to 1 mole. Now mole fraction of gaseous mixture at 100 degree centigrade. Now here that gaseous mixture is there, and then 100 degree centigrade. Okay, and 100 degree centigrade, and maybe okay. So in that 100 degree centigrade we have to calculate mole fraction. So now here suppose we have gaseous mixture containing two gas A and B, 100 degree centigrade. The mixture contains 3 moles of gas A and 5 moles gas B. So similar, x A moles of gas A, total moles of mixture. So Na by Na plus B. So 3 by 3 plus 5, 3 by 8, 0.375. Similarly xB, 5 by 3 plus 8, so 0.625. So again xa plus xb, that will be 1. So xa will be 37.5% and B will be 62.5%. We can convert mole fraction to percent. Now here volume conversion at STP. Now suppose we have a gaseous mixture containing two gases A and B at 100 degree centigrade and 1 atm pressure. The mixture is in a container with a volume of 24 liters of gas A and 50 liter for gas B. Now how do we calculate mole fraction? So to convert the volumes of for 100 degree centigrade and 1 atm to STP condition, 0 degree centigrade and 1 atm, so we can use P1 V1 by T1, so P2 V2 by T2. Now P1 is 1 atm, V1 is 24 liters, and T1 is 100 degree centigrade 373.15. Now when we take the STP, so we can get what is A at STP, so that we can calculate the next slide. So V2 will be actually 70.4 per liter, and similarly we can calculate the final volume of V2 for gas B. Similarly V2 P1 V1 T2, so that is 36.20 liters. So we plug all this value, after we will get that the volume of at STP condition approximately 70.4 per liter of the gas A and 36.20 liters of gas B. Now we know at STP that 1 mole gas contain 22.4 liter. So from that we can calculate, so number of moles of A, so that 70.44 by 22.4, so that is 0.780 mole, and number of moles of gas B, so that is 36.20 by 22.4, so 1.616. so we can do that. Now after getting the mole, so we can calculate the mole fraction. So moles of individual component by total mole, so 0.780 by total mole, so that is 0.360. xb, so 1.616 by total mole, so that is 0.674. so from that we can say that in the gaseous mixture at 100 degree centigrade and 1 atm pressure, the mole fraction of gas A approximately 0.326 means 32.6%, and the mole fraction of B gas approximately 67.4 means 67.4%. So that's it for today. If you have any question, any queries, you can contact me through email, or you can send message in the YouTube comments. Thank you.